Hello everyone. Our project is titled Interactive Mock Interview and Feedback Tool Using AI. We developed a system that simulates job interview feedbacks using advanced models like Cobalt for natural language processing and Whisper AI for speech recognition. Here's the outline of today's presentation. For many college students, preparing for job interviews is challenging due to the high cost of professional coaching. We identified the need for a cost-effective, AI-driven system that provides real-time interview feedback anytime, anywhere. The transformer is a neural architecture built on attention mechanisms and feed-forward layers designed to overcome the limitations of RNNs. It processes all tokens simultaneously using self-attention, allowing it to capture long-range dependencies and enabling faster parallel training. The core design is an encoder-decoder structure. Encoder powers understanding tasks like classification, while decoders drive text generation. Whisper is an open-source speech recognition model by OpenAI that transcribes and translates audio in many languages. We chose Whisper because it handles noise and accents well, supports Korean, and is free and easy to use. Whisper uses a sequence-to-sequence transformer model. First, the audio is converted into a spectrogram, which is a visual representation of the sound. This spectrogram is then passed through a series of encoder blocks, and the decoder generates text tokens step by step. This design allows Whisper to handle tasks like speech-to-text, translation, and alignment. Cobalt is a sequence-to-sequence transformer model based on the BART architecture. It combines a BERT-style encoder for understanding context and a GPT-style decoder for generating text. What makes it special is that it's pre-trained on Korean data, so it's well-tuned for the linguistic features of Korean language. Now, let me explain how Cobalt works. First, during pre-training, the model learns to restore original sentences from corrupted input, helping it understand Korean language patterns. Next, the sentence is tokenized into subwords using sentence piece, enabling efficient handling of Korean words. After tokenization, each token is embedded with token and position information. Then, the encoder processes embedded tokens bidirectionally to capture context and understand the sentence meaning. The decoder generates the output token by token using encoder context and previous tokens until the sentence is complete. Finally, the model detokenizes generated tokens into readable Korean text as the final output.
By using a Cobalt model fine-tuned on interview data from AI Hub, it is possible to implement a function that summarizes interview responses. When a single sentence, rather than the entire interview, is used as input, the model tends to refine the sentence in a way that aligns with the context of a job interview. This property can be leveraged to evaluate how appropriate a given response is within an interview setting. Since the BART model is an advanced architecture built upon the transformer model we studied in class, we wondered whether we could achieve similar results by developing our own transformer-based model. With this in mind, we attempt to do so. We first trained a basic transformer architecture on the interview summarization dataset. As training progressed, the training loss continued to decrease, but at a certain point, the validation loss began to increase, indicating the decline in generalization performance. Based on this observation, we assumed that the dataset was insufficient in size and decided to apply token masking-based data augmentation as a first step. We could clearly observe that both training and validation loss decreased. Next, we applied token deletion and text infilling, which are data augmentation used in the BART model. These methods also led to further reduction in loss, indicating improved performance. We also applied position-based data augmentation, This includes sentence permutation and document rotation. Both methods had a positive impact on performance. We replaced the post-norm transformer architecture with a pre-norm transformer. As a result, the training loss decreased more effectively compared to before, indicating better learning on the trained data. However, the validation loss still didn't improve, indicating that the overfitting issue remained unresolved. In addition to this, we tried various approaches such as increasing the drop rate and sharing embeddings between the encoder and decoder, but the generalization issue still remained unresolved. Ultimately, increasing the amount of training data turned out to be a most effective way to improve generalization. As the dataset grew, we clearly observed improved generalization performance. We wanted to experiment with a much larger dataset, but the training time became excessively long, and the limited GPU memory available on Corep made it difficult to proceed. It's a bit disappointing that we couldn't explore a wider range of approaches to further develop the model. We hope to study more and achieve better results in future experiments.
Although it's a bit unfortunate that we couldn't use the transformer architecture we developed, we'd like to introduce the feedback tool we built using our fine-tuned cohort model. First, the spoken answer is transcribed into text using Whisper AI. Then, the text is split into individual sentences using the KESS library. Each sentence is passed through our fine-tuned cohort summarization model, which preserves the core meaning while removing filler words, redundant expressions, and awkward endings, producing clearer and more concise sentences. To evaluate how well the refined sentence aligns with the original, in other words, to assess whether the original answer was well structured, we used 3 types of similarity metrics. The first is semantic similarity, calculated using sentence part. This model converts sentences into high-dimensional semantic vectors and uses cosine similarity to measure meaning alignment. Since cohort typically preserves meaning well, this score is often above 0.9, so we assign it a lower weight. However, if the score is below 0.8, we consider the summarization invalid and exclude the sentence from evaluation. The second is word similarity using TF-IDF. This evaluates word-level similarity, how the sentence is expressed. If a response contains filler like or repeated or awkward phrasing, the wording difference increases, leading to a lower similarity score. The third is structure similarity using Levenstein distance. This metric compares sentences at the character level, counting how many characters must be inserted, deleted, or replaced. It reveals structure differences such as length changes, word order shifts, or removed redundancies. We then compute an overall similarity score by taking weighted average of the 3. If the score exceeds 0.7, the answer is considered appropriate. Otherwise, it is inappropriate. Now, let me walk you through some examples. In the case of well-formed interview answer, the refined sentence usually differs very little from original, and all 3 similarity metrics score high, leading to a judgment of an appropriate response. In contrast, if the sentence repeats certain conjunctions or includes filler expressions such as the similarity scores tend to be lower, helping us identify such expressions need improvement in an interview setting. Additionally, for very short responses, the cohort summarization may not work properly and often yields low semantic similarity. Therefore, if the semantic similarity score is below 0.8, the sentence is classified as not evaluable. Through this process, each sentence in the response is evaluated, and any inappropriate sentences for an interview setting are identified and refined accordingly. This concludes our presentation. Thank you for your time and attention.